Welcome back again. Yesterday we were talking about ideals of a ring, and we saw that an ideal is need may or may not be a subring. Okay, so in case if they are subring, then it gives more properties or more interesting properties. And today we are going to see some particular type of uh, ideal. They are called, one is the prime ideal and another is maximal ideal. The name suggests something that we will know when we see the definition of these ideals. Okay. So what we have seen yesterday is that if R is a ring, okay, and S is any subset, okay. So S is any subset, then S becomes ideal. S becomes ideal if A minus B belongs to S, okay, and RA as well as AR belongs to S. For all A belongs to S and R belongs to capital R. So if this satisfies, this subset has satisfied these properties, then we say that S is an ideal of R. All right. And moreover, if S becomes a subring, if S is a subring, then the only things we need to prove that RA and AR belongs to S for all A belongs to S and R belongs to capital R. So when R is subring, then only we need to see that closer or once or what we need to see that AR, okay. And of course, because S is subring, so product of any two elements of S is going to be in S, and the difference of any two elements of S is going to be in S only, okay. But we are not sure about that if we are taking R from capital R, okay, which may or may not be a member of S. If R, small r, is a member of S, then all right. Then every subring becomes what? Every subring becomes uh, uh, an ideal, okay. But that is the case. In that case, what happened that S will become exactly R, okay. So what we conclude that that ideals that is zero, having only zero element, one ideal, okay, and another ideal is the ring itself. So there are at least two ideals, okay. That's what we know. Fine. So now, okay. So we can note it down that let R be a ring. Let R be a ring. Uh, let R be a ring. Okay. Then 0, that is that 0, the set containing only 0, and R always an ideal. Always ideals, okay. Always are always ideals of R, okay. So this is one note. And what other things we can have here? We have also seen in case of example, in case of the set of integers, okay. So we have seen the example, the set of integers. Uh, Ideals, if we talk about ideals, so their ideals are of the form I equals to mz. So because you know that every subset of or every subgroup of Z are of the form mz, and all those subgroup, or we can say subset, they are ideals. Okay. So this we have seen yesterday, that how we can prove that NZ is always ideal. Okay. Or we can say that every subgroup of Z, every subgroup oblique, we can say subring of Z is an ideal. Okay. So next is let us see next example. Question is that uh, is every subring of Q, the set of rational numbers, is every subring of Q an ideal? So this is a question. So of course, if you talk about the subgroup, then the difference is going to be a rational number if we are taking any two rational number. Okay. Because subring is guaranteed here. So what else we need to verify? This thing that here what we have written, that AR and RA should be in, that is should be two-sided ideal. Okay. So if you take here, for example, I think we can take Q is the rational number. So of course, Z is a subset of Q, Z is a subset of Q and Z is a ring. Okay. The operation or operations on both set are the same when we consider the ring. Okay. The usual addition and multiplication. Okay. So this is a what we call subring. Z contained in Q is a subring, but not an ideal. And the reason behind this is that the close when we talk about when we consider A times R or R times A, then we may not be having the final product is to be in Z. So for example, if you take 2 belongs to Z, and 1 by 2 or 1 by 3, whatever. Okay, 1 by 3 we can take, not 1 by 2. 1 by 3 belongs to Q, but 2 times 1 by 3, and this is nothing but A. Okay, and R is our Q. So A times R equals to 2 by 3, and this is not a member of Z. So this is a subring, but not an ideal. Okay. So next, let us see. Let us see something quickly. Next are example, but not example. Example come result. We can say, okay, result. So result is that every subring, every ring are, okay, let us write. If R is a ring, if R is a ring and A belongs to R, then I, which is generated by A, this is a natural subset. Okay, generated by A is an ideal. Okay, is an ideal of R. So corresponding to each element of R, we have an ideal. So this is one of the interesting result. Okay, and this you can prove. Let me give you a hint only. Okay. Hint is that when you are defining A, this is generated by I, this is generated by A, and this is going to be a collection of the elements of the form like this, where n belongs to n belongs to the ring, just a minute, no, no, where A belongs to, where A belongs to the ring, okay. And of course, you know that n is an integer, no? It is integer. And then you can now everything you can verify. The difference you can take a n1 minus a n2, okay. Then you can take common n1 minus n2. Of course, this is going to be another integer. All right. So you can write a n3, and this belongs to where? This belongs to I. Okay. So similarly, you can verify. So one thing we have also noted next, the result I'm going to write. Okay, this you can also prove that uh, I equals to 0 and I equals to R. Okay, are always ideals of R. Okay, so this you can prove, that is every ring has at least two ideal here, unless it is identically zero only. Okay, so if your ring has only one element, that is zero, then there will be one only. Otherwise, if it is non-trivial, then it will have at least two ideals. Okay. Uh, so, for example, if you talk about the ideals of Q, you know, so ideals of Q are 0 and 0 and Q itself. Other you can find it out if you find if you want. Okay, but we are not sure about whether there are only one or two. So that we will refine our result later on. Whether in what condition we have only one ideal or two ideals. Okay. So in case of a set of Gaussian integers, ideals are you know 0 and this itself. Okay, so at least two you can write. Fine. So in case of the set of real numbers, also we have ideal. One is 0, another is the set of real number itself. Okay. So these are few examples I was talking about. Okay. Now the question. Okay. Another important result is that uh, when ideal becomes exactly the ring. Okay. Okay, if some ideal is given, in under what condition that ideal will be exactly that of the ring. Okay, so that next result gives information about this, and this says that if I is an ideal, is I is an ideal of R, of course R is a ring, and one belongs to the ideal, that is it contains an identity element. Of course, because being an ideal of R, it means that I must be a subgroup, a subset at least. No, at least it should be a subset. And because and one belongs to identity, that this ideal, it means that one also be a member of R. That is, R is a ring with unity. Okay. Yes, R becomes identically to R. Fine. So this you can verify. You know that one way you can directly say that I is a subset of R because it is an ideal. Okay, and then other way you can take R belongs to capital R. Okay, R belongs to capital R, and one belongs to the ideal, and therefore R times one should be in ideal, because by the definition, because of the definition of an ideal, it should be right ideal as well as left ideal, and therefore this implies that R is also member of I. So we have taken in small r in capital R, and we are concluding that R belongs to the ideal. So it means what? R is a subset of I. Okay, I, that is ideal. So from 1 and 2 together implies that R is equals to the ideal itself. Okay. Okay. Now next, only a few things I'm going to give you a formula for this. So question is that can we determine the number of ideals? Okay, number of ideals. So in particular case, I'm giving you hint. Okay, number of ideals. Ideals. Uh, ideals of Zn. And this formula is going to work for this Zn. Okay, so uh, the number of ideals is going to be tau n. That is, this equals to the number of divisors. Okay, number of divisors of n. So you need to count. Okay, so for example, if you are taking R as a ring Z12, okay, so how many divisors are there of 12? Divisors of 12. I'm telling you some numerical examples also, so that uh, you can what yeah, you can prepare for competition, or you if you are seeing some papers of a competition or exam, so you can find it out. Okay, what are there? So actually they sometimes they want this kind of numerical, they put this kind of numerical question. Okay, so divisors of 12 are, what are they? 1, 2, 3, 4, 6. What else? 12. So how many? 6. No? 6. So tau 12 is equals to 6. So there are going to be 6 in numbers. Okay. But thing is that if this number is bigger, then how we can compute? Okay, if n is bigger. So there is a formula that tau n. Okay, how to calculate tau n. For this, you know that every positive integer can be written as a product of natural numbers. Sorry, can be written as a product of primes. Okay, uh, uniquely is except order. Okay, right. So we can write, just for example here 12. We can write 2 times 2 square 3 3 to the power 1. Okay, so here a power is 1, here a power is 2. Just add 2 plus 1, and here 1 plus 1. So 2 plus 1 3, and 2 1 plus 1 2. So 3 times 2, that is going to be 6. Okay, so in general, if you are having some natural number n, and this power is alpha 1, and then another prime p2 power alpha 2 dot dot dot, and power pr to the power alpha r, pir primes. Okay, pir primes. Then tau n is equals to alpha 1 plus 1, alpha 2 plus 2, and dot dot dot, alpha r plus alpha, no, here not 2, here 1. Okay, everywhere 1. So this is a formula for this. Hello. Okay.
Yes, sir.
Okay, so in particular case of Z12, let us see what are they. In Z12, you know that ideals, एक तो क्या होगा, मतलब खुद ही होता है, जीरो होता है ना, जीरो. One is 0. All right. Another is what?
Z12.
Another is 1. No. And 1 is nothing, but it is generating whole set. All right. Okay. This is Z12. Na? Z12. The way you are saying. So we know 2. Now we need 4 more. So next 2, we can take 2, we can take 3, we can take 4. Okay. So they are ideals. Okay. So this 2 contains the element of the for 2 times Z12. Yesterday I was telling what are their ideals. No? So this is 3 Z12 like this. Okay. Fine. So it means that every element you have to multiply with 2 and then reduce it to multiplication modulo 12. Okay, so this one is 4 times Z12. Okay, similarly, and don't we get confused that sir is taking only those number which are divisors, but of course I have written, I have also taken 0, and next I'm going to take 5. This is also going to be an ideal. Huh? So this not 5, but no, not 5. This should be 6. Okay, corresponding to divisor. Okay, except this one. Everything I'm going to take divisors only. So here this is 6 times of Z12. Okay. So 1, 2, 3, 4, 5, 6. I think everything we have concluded here. Everything we have enlisted here. Fine. So if you will be asked what are the ideals in case of ZM, I think you can find it out. हाँ? पक्का कोई दिक्कत नहीं? Hello.
Yes, sir.
Yeah. In case of Z100, N is 100 ना? So 100 को कैसे लिख सकते हैं? 2 to the power 2, 5 to the power 2 ना? Okay. So tau 100 is equals to what? 2 plus 1 and 2 plus 1. So 3 times 3, this is equals to 9. So there will be 9, no? 9 ideals of Z100. So 2 you know already, 7 you need to find it out. What are they? Okay. Okay, let us see next. So we have seen enough example, I think, on ideals. Now let us talk about something ideal, something about ideal by putting certain condition or on the basis of their nature of the elements. Okay, sometimes we put some restriction on them. So how we define ideal? We say that a subring is going to be ideal if it is left ideal and right ideal. That is AR and RA and AR. This both should be in S. Okay, but natural question is that if we have some two product of any two elements which belongs to S, is there any guarantee that A belongs to A is going to be in S or B is going to be in S? So this was the question. Okay. So with this extra property, an ideal is called the prime ideal. It's called the prime ideal. So this says that prime ideal. Okay. And the maximal ideal, there is another concept. Maximal ideal, the name itself suggests that suppose I is an ideal of R. Okay, I is an ideal of R, and this is contained in I R. Okay, so when we say that this is the maximal, if there is no ideal between these two, okay, if there is no ideal between these two, that is, there is no ideal which contains I and contained in R. Are you getting? There is no ideal between I and R. Then we say that ideal I is a maximal ideal. Okay, so let us see what is the maximal ideal, official definition, and then we can talk about some examples and then prime ideal. Okay, so what is maximal ideal? So let R be a commutative ring. R be a commutative ring. An ideal, ऐसे a proper ideal. Okay, and occur ऐसे लिखते an ideal, say A, okay, which is not R, Okay, it means I mean to say that this is going to be a proper ideal. Thing is that no, either I should say that it is a proper ideal, or I should write that A is not R. Okay, is said to be said to be maximal ideal of R if there exists an ideal B in R such that A contained in B contained in R, then either A equals to B or B equals to R. Fine. That is, or let me write in language, that is, there is no ideal containing A and contained in R. There is no ideal between A and B, between A and B, which is containing A and contained in R. Okay. So if at all we are going to get any ideal B, so this should be either A or this B should become R. So it means that there is no ideal between A, B and R. Maximal, that is in one sense अगर हम numbers में बात करें तो मैं कहते हैं maximum number है ना, supreme हम बात करते हैं किसी set का. If exists, it is unique, you know, something like this. It is the biggest ideal. Okay. No ideal can contain that one, okay, except R. Okay, all right. So example, we can see. Example is that if you take Z6, okay. So for Z6 ideals, what are the ideals? Tell me. One is 0, another is Z6. So they are they are trivial in one sense. Okay. So other ideals, hey, take elements from here and multiply. Fine. Okay. So what are the, in one sense you can take the divisor of this one. So 2Z. Okay. 2Z6. That is 2. This is going to be 2 times Z6. Okay. This is going to be an ideal, and then generated by 3. And this is going to be equals to 3 times Z6. Okay. And Z6 is there. So there are 1, 2, 3, 4. And you know, top 6 equals to, you can write now 6, 2 times 3. So 1 plus 1, power, both power is 1. So 1 plus 1. So how 2 times 2, that is 4. Now to total 1, 2, 3, and 4. Only 4 ideals are there. Okay. So what is maximal? You know that 0 is there and Z6 is there. Now in 2Z6, this is generated by 2. What are the elements? 0, 2, and 4. The product of 2. Okay, multiple of 2. And in 3, what we have? We have product of 3. So 0 and 3. Fine. Hello. So if you say this is I1, okay. So what can you tell me any sequence of these ideals? Hello. Hello. Which ideal is maximal ideal? Hello. Okay, let us is nothing but 0, I1, okay, and then I2 is I2 is uh, the ideal generated by 2, that is 2 0 2 4 0 2 4, okay, that is 2Z2, okay, 2Z6, okay. Then I3 is generated by 3, I4 is equals to Z6, fine. So can I4 be maximal? No, okay, because uh, maximal ideal should not be equal to the ring itself, okay. First, what is Z6 is not maximal, okay, is not maximal. Second, Z6 that is I4 na, I4 is not maximal. So what we need I1, I2 and I3. Three need to be verified. So I1 is maximal. So I1 is 0 and 0 is contained in I2 and this contained in uh, Z6 na, I2 and okay, it is in Z. Okay, there is, I think, there is no containment relation between I2 and I3, है ना? Okay, so this is Z6, fine. So I3 because I1 cannot be maximal because we have one ideal which is containing I1 but contained in Z6. So I1 cannot be maximal, na? I1 is not maximal. I1 is not maximal. Third, what we have seen that I4 and I1. Now we are left with two more. So let us consider that I3, whether I3 is maximal or not. So I3 we can consider. So ideal, of course, I3 is contained in I3 is contained in Z6. So is there any ideal in between these two? Because we have only 4 ideals for this set, this ring. Is any ideal? Hello.
No, sir.
Here this and there is no ideal between I3 and Z6. Okay, so this becomes I3 is maximal. So question is that should we stop or should we check I2 also? Is maximal unique? Hmm? Very first glance में लगता तो है, but it is not true. We got one maximal ideal I3. Let us see. Let us take I2 also. Okay. So uh, I2 is such that I2 contained in Z6, you know. Yeah. And what other ideal? Is there any ideal between I2 and Z6? That is a 2 4 6. Okay, this ideal is not contained. Okay, then we have this one. Of course we have another ideal here, what we say that I1, no, like this. So because there is no ideal between these two, I2 and Z6, so Z6 becomes, sorry, I2 is also a maximal ideal. Okay, so in a ring, in a given ring, we may have more than one maximal ideal. In very first sight, in very first glance, ऐसा हमें feel होता है, we feel like that because the word is maximal is used, so there should be unique kind of thing. Okay, but it is not like that. Maximal may be more than one maximal ideal. So that's why here in the definition is said to be maximal ideal. We have not written the maximal ideal. Okay, so maximal ideal may be uh, more than one. Fine. Is it okay? Or you have any doubt? Next example, you can find maximal ideals of in case of Z8. Okay. Okay, let me leave it. I was thinking some more examples. Okay, so I think you can practice it. Okay, later on we will see if we can find it out. In case of Zn, we can have some guess what are maximal ideal. Okay. Okay. So let us see further. Um, we can have a now we can see the prime ideal. Okay, and then after we can have example on it. What is the prime ideal? Next, prime ideal. Let R be a commutative ring. Commutative ring. An ideal A is not equals to R is said to be prime ideal of R if AB belongs to P, belongs to R, implies either A belongs to R or B belongs to R. So if the product in R, then at least one of them is in R. So in that case, we say that that ideal is a prime ideal. Okay. So some examples we can note down. Ideal, if you write the zero containing only zero element, is prime ideal of uh, of the ring of integers. Okay, so this is very much true. You know, if you are taking any element A and B, uh, just a minute. If I have done something, I think an ideal A, I have written A here, so I am writing R. Okay. Here, I'm sorry, this should be A, no? This should be A. Okay, this should be A. So if we are taking A, B belongs to this I, okay, and A, sorry, not AP belongs to I, but uh, left we can take A, B belongs to the set of integers, and A times B equals to 0. This belongs to I. So this means either A is 0 or B is 0. So this is very much clear from here. Okay. Next, if we can take 0 is a prime ideal of the set of Gaussian integers. Okay. More examples. If you take Z, next. So many examples we have in Zn. So if you're taking Z30, so question is that whether 0 is a prime ideal of Z30. Okay, so that we need to check. Okay, is 0 a prime ideal of Z30? Okay, so this is the question. So sometimes we find that a 0 is there. Okay, so this should be prime ideal. Okay, so but the thing is that we need to be careful. In Z30 we have 5 and we have 6. Okay, the 2 belongs to Z30. 5 times 6 equals to 0. That is 30, and this is equals to 0. This belongs to this set. Okay, this ideal. But thing is that but this doesn't imply 5 is 0 or 6 is 0. Okay, इम्प्लाई नहीं कर रहा है, ना तो 5 0 है ना तो 6 0 है, तो इसका मतलब क्या है कि वो प्राइम आइडियल नहीं है. So it means what? This implies that 0 is not a prime ideal of Z30. Okay, so 0 can be a 0 can be an ideal, but whether it is a prime ideal is it is not necessary that it is a prime ideal or it is a maximal ideal. All right. Yes, 0 is prime ideal in one case. So that result we can note down. Okay. Uh, let R be an integral domain. Let R be an integral domain. Then 0, this trivial ideal, is always a prime ideal. Okay, always a prime ideal. So so with the help of this we can note what we can note that I, that is 0, if you take, is prime ideal of what? Set of integers, set of rational numbers. Okay, R, set of Gaussian integers, set of complex numbers. Okay, so 0 is because they are integral domain. So in that case, 0 is necessarily is going to be a prime ideal. Okay. Next note, of course, I'm not going to prove it. If R is a field, I'm imposing more restrictions. Okay, if R is a field, then R has exactly one prime ideal. Prime ideal 0. Okay. So in case if the ring becomes filled, then there is only one prime ideal, that is 0. Okay. Next, I'm giving a question to you. You can try to prove it. Next result, and this result says that so that, and this question may be an exercise problem also. So PZ is prime ideal of Z, where P is a prime. Okay. All right. So this you can try it out. Okay, fine. Some more thing I wanted to tell you. Number of prime ideals. Okay, number of prime ideals. Uh, number of prime ideals. Number of prime ideals in Zn. Number of prime ideals in Zn. This is equal to the number of prime divisors of n. The number of prime divisors of n. Okay. So in case if you are considering Z12, okay. So divisors, first you have to write divisors of 12. So what are they? 1, 2, 3, 4, 6, and 12. No? So how many of them are primes? This one, 2. There are 2. No? Only 2 primes are there. So number of prime ideals. So Z12 has 2 prime ideals. Okay, that you can find out. Is it okay?
Yes, sir.
Fine. In case if you take Z16, then so divisors is K 1, 2, 4, no? And 8. What else? 16 or anything else? 16, no? Hello.
Yes, sir.
So how many prime divisors? Only one, no? One. So Z16 has only one prime divisor. So अभी एक हम लोगों ने रिजल्ट नोट डाउन किया है ना? What result we have noted down that in case of prime ideal, in case of if a ring is filled, then we have exactly one prime ideal, that is 0. No, this 0. So can we talk something converse to this? Suppose if there is only one ideal, that is a 0 ideal, then is it necessarily that ring is filled? तो जैसे यहाँ पे केवल एक प्राइम डिवाइजर है ना, केवल एक ही प्राइम डिवाइजर है और इसलिए केवल दिस इज ओनली वन प्राइम आइडियल ना, प्राइम आइडियल. फाइन. तो क्या Z16 फील्ड बनेगा या ये प्राइम आइडियल कौन सा होगा, 0 होगा या कोई और होगा? ठीक है ना. So this need to be taken care of.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning! through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.